Okay, so in this section of the module, we're going to talk about sample versus global population. So in the last, uh, uh, I guess, mini lecture, we learned about the different ways we can describe a population: the center, the mean, the median, the mode, the spread, the standard deviation, and the variance. But for all of those, we were talking about the population parameters. But most of the time, you're not going to end up working with populations. You're going to end up working with samples that you draw from that population. These samples will be some subsection of the total population, and the samples themselves will have mean, medians, and modes, and standard deviations and variances. But we talk about them in a slightly different way than we do the population. This is where estimators versus estimands comes in. Estimands are what we've been talking about up until now. They're also called parameters. Last lecture we learned about ways to describe data, the mean, median, and mode, standard deviation, and variance. And all of these describe characteristics of the population. These are all population parameters. But how are these determined in real situations? As I've mentioned before, you're probably going to end up taking samples. And these samples are estimators of the global population parameters. So estimators provide an estimate of a population parameter. They're also called statistics, which is why statistics is called statistics. And yeah, these are useful because we almost never have the resources to sample an entire population. In many cases, it's even possible to do it, even if you had infinite resources. So these estimators are what we'll be dealing with for most of statistics, because the population parameters are usually inaccessible. We're always estimating those with the stats. Okay, so say we have a normal distribution of twigs that we find in a forest. This normal distribution has a mean of 5. Our probability for finding a stick in a particular forest of length L is represented here. This probability distribution represents the entire populations of sticks in the entire forest. But if we were to go, say, sample 4 sticks, we would get a sample from this global population. So say we randomly sample 4 sticks. I put some dots here to represent them. And I said randomly sample. So random sampling is another key term that I'm throwing at you here. And this means that each member of the population has an equal likelihood of being sampled. True random sampling is sometimes hard to accomplish in studies. There can be biases of the studies people will talk about by age group, or most of the complaints that you find in correlative studies is that there's not true random sampling. So if you're following the election, right, pollsters spend a ton of time trying to make sure that their random sampling is truly random and a representative of the entire population. And that can be really hard to do because people don't pick up their phones, different demographics do it at different rates, things like that. And whenever you don't have random sampling, it will skew your estimator, which will skew your perception of where the population parameter is. Okay, so the average of these 4 values is always going to differ from the actual population parameter unless you've sampled infinity times or the entire population, right? If you're doing a subset of the population, it's invariably always going to be different than the true population mean. So remember your coin flip experiment? What happened when you flipped more and more, right? This green line would trend more and more towards the blue line if we sampled more and more twigs, just like as you flipped more and more coins, it would trend more and more towards 50%. So if we sample infinity sticks, as I said, the average of the sample will trend towards the population mean. And estimators, yeah. So the next thing we'll talk about is that estimators have their own nomenclature and formulas in some cases. So I made this helpful table for you. We have our mean and our variance and when to use them. And over in this column in blue, we have our population, our estimands, both the variable and the formula that you use. So for mean, it's what we saw last time. It's mu, and it is the formula we saw last time, which is adding everything up and dividing it by the total number. For variance, we have sigma squared, and 1 divided by n, and then you add up all of the squared differences between the mean and each point. And you're going to use those when you want to calculate a parameter given the entire population of data, if you happen to have that, every single thing in an entire population. But that's going to be exceedingly rare. You can never do it for all of the people or really even all of the twigs. Okay, so now let's talk about it for sample, an estimator. So now the mean is going to be represented by x bar, and this denotes that it is a sample mean. You'll notice that the formula is the same as it is for the population mean, but the variable that we use is different. And for variance, instead of sigma squared, we're now looking at s squared. But you'll notice over here that the formula is slightly different. You still sum all of the differences from the sample mean, but you divide by n minus 1 instead of dividing by n. So you're going to use these when you want to estimate a parameter given a random sample of data from a larger population. But what's up with this n minus 1? Why are we not using dividing by n here? Why are we now dividing by n minus 1? And it all has to do with the fact that we're using x bar here in this equation instead of using mu. So this all comes down to having a good understanding of degrees of freedom. So what are degrees of freedom? It can be defined as the number of values in a calculation that are free to vary, minus the number of parameters being estimated or constraints that you have on the system. So say we go back to our normal distribution. If we were going to take a sample from there, and we selected 4 random sticks, each of the sticks is free to be whatever value it wants. And therefore, for 4 randomly selected sticks, there'd be 4 degrees of freedom, 1 per stick. But the rub comes in that a degree of freedom is lost for each parameter that must be estimated from sample data. And so for statistics, if you look things up online, it's often simplified as the degrees of freedom equals n minus 1. It's simplified to degrees of freedom equal n minus 1 for most statistical analyses because nearly all statistical analyses are going to require some estimate of the mean. They're going to require x bar. And since x bar is an estimate, it's depriving the sample of one of its degrees of freedom. So the degrees of freedom equals n minus 1. For some more advanced tests, really interesting ANOVAs that you can do, there can be even less degrees of freedom. But for this course, you can mostly assume that if you see something and we're running statistics on it, the degrees of freedom are going to be n minus 1. And I posted a really nice paper describing this in detail if you want more background on what degrees of freedom are and how they apply to different statistical tests. Okay, so for example, if we're calculating the sample variance, sample mean must already be known. So if we have our 4 sticks, x1, x2, x3, and x4, and we know that our sample mean is going to be 5.3, then by the time we get to this last sample, x4, it has to be 7.2 in order for our sample mean to be 5.3, and therefore x4 has lost its freedom, and that's where the degree of freedom is lost. So let's go back to variance and deal with this n minus 1 for sample variance. And I said it all had to do with the x bar, which you should be getting an understanding for now. And we have our randomly selected sticks. If we were using mu instead of x bar in this equation, right, the true mean instead of x bar, then when we took our samples, the x4 could still be anything that could be any number, right? Because we weren't using an estimator to estimate a parameter. And so x4 could still be any number in the entire population. But if we're using x bar, that means we have already done an estimate to get x bar into this equation, and therefore the final thing, x4, would lose its degree of freedom, right? And so for these reasons, for variance and for most other statistical calculations, you will use n minus 1 as your degrees of freedom. And if you want more information on this, there's a nice paper that I'm posting to the module in this where the PowerPoints are.